Hi, my name is Justin Park, and today I'll be presenting some of my ideas about how to revolutionize the world, more specifically, the private space industry. I've given earlier iterations of this presentation at the International Astronautical Congress in Glasgow, Scotland, and to the Russian Executive Council in Moscow, Russia in 2008. Since that time, I have stumbled upon some setbacks, but also some newer, more promising technologies that have helped me realize that it is within our power to create an almost completely renewable orbital launch process. Although I would consider myself a computer scientist by trade, my true passion now lies in an area far more important than what can be represented by a long string of ones and zeros. Throughout my academic and professional career, from the University of Iowa to the Egan-Ganesh Technische Hochschule in Zurich, Switzerland, I have learned from hundreds, if not thousands, of brilliant scientists, engineers, and consultants. But more importantly, while at the International Space University and at NASA Ames, I was given the unique opportunity to meet dozens of passionate astronauts, geniuses, and aerospace directors. They instilled into me a similar infatuation with what is beyond the atmosphere. Unfortunately, for a long time, most of outer space has lied dormant because it has been so incredibly dangerous and expensive to reach. Humanity has been so focused on short-term solutions to fix Earth that it has failed to see beyond the horizon. Ironically, what we need is a gun. Although I've encountered many talented individuals throughout my career, in general there seems to be a disconnect between the rocket scientists and the capitalists wearing suits. It is my belief that we already have the materials and most of the knowledge necessary to build an electromagnetic propulsion system that is completely capable of consistently firing materials into orbit. The only real constraints seem to be financial and political. For this reason, I will begin by discussing the business side of my research. This isn't to say that the engineering portion isn't important. Quite the opposite. My goal is to actually inspire the scientific community to help me. I've realized that trying to design everything by myself is not only impractical, but just plain ignorant. There are many specific components, materials, and mathematical details that still require a great deal of in-depth research. With the advent of open source projects, I encourage you to visit www.01foundation.org after this presentation and contribute any published papers or research you might have regarding this topic. The 01 Foundation is also taking proposals to manufacture individual components. Lastly, feel free to contact me directly at justin@justinpark.com if you would like to become a 01 Foundation member. So the first question is, who is going to fund this project? These three individuals, Bill Gates, Warren Buffett, and Carlos Slim, could do it themselves. However, angel investment is highly unlikely. Historically, most space companies haven't had very successful track records. This discouraging fact seems to have ingrained a sense of deterrence in the venture capitalist community. A large international public-private partnership, or PPP, is the only logical way to come up with the funding necessary to create such an expensive device. Here are just a few of the companies and organizations that should be involved. They have the expertise. It is also likely that the current demand for small to mid-sized traditional rockets will cease to exist completely once this type of electrical cannon becomes operational. So it is only natural that existing aerospace firms be involved. That way, when the streams of revenue shift, those invested will actually be part of the new launch paradigm. Without going into too much detail about how the credit works, I think it is important to at least explain what it is. I'm proposing that a new, completely digital currency be used for conducting commerce in space. If the World Bank, WTO, and International Monetary Fund would come together and manifest such a financial system, it would allow the industry to function in a new way that is conducive to all countries. If you would like to learn more about the credit, I would recommend reading my newest novel, On the Verge of Space, which can be found on my blog, justinpark.com. Now, some people may laugh at this slide because it points out the irony in one of NASA's greatest problems: lack of corporate advertising and sponsorship. Organizations and companies that operate in space need to take advantage of the capital that can be generated there. Product placement is an industry in its own. Telecom service providers can exchange broadcasting time for launch services because it is also important that an appropriate marketing campaign take place as the propulsion system is being built. People need to know that space is accessible. And let's not forget, at the center of the diagram lies the credit. Here are some highly approximated fixed costs. Although these financial figures are not 100% accurate, what I really aimed for here was just a general sense of the orders of magnitude that we are dealing with. This is the cost of materials and labor required to build the actual EMP system and all of its subcomponents. I anticipate hundreds of small RFPs will be used to divide the work up appropriately. you'll notice that I gave two separate cost breakdowns along with the acceleration associated with the two potential lengths of interest. Note that at 5.2 Gs, the rate of acceleration is subtle enough that it would not cause bodily harm or discomfort to the average person with high speed and acceleration training. Some of the recurring costs include the nuclear energy used to power the lasers and magnets. There also needs to be money for staffing and the small nanorockets used in the second stage of the launch. I pulled some numbers from the CERN Particle Accelerator website just to get an idea of what the annual expenditure could be. Revenue for this system will come from many different places. To ensure the greatest constant income stream, launch slots will be auctioned off to the highest bidder several months in advance. If you look at the current launch costs, one can predict that originally positions will be priced very high, around $25 million per use, but will eventually dip down to just several 100,000 credits per launch as the queue begins to thin out. Governments, including those in developed nations, along with independent companies, will make up the bulk of the consumer base for the first several years, with university and research groups in the years to follow. After commercial facilities exist, I anticipate travel agencies will buy in bulk to facilitate a richer customer base. Those individuals who want to experience weightlessness in lower Earth orbit, space station, module, or modules. The estimated return on investment for the large EMP is approximately 25 years, but could be longer or shorter based on the demand of the launch industry. The last important financial element to talk about are the spin-offs. There is a vast array of wealth to be made in the wide range of technologies that come about from space. This type of affordable access into orbit will revolutionize what can be done there. I'm talking about everything from drop tower experiments to long-term duration missions to the surface of the moon. It can be used trivially to launch telecommunication satellites or resupply to the ISS and other independent private space stations. It could be used for expedited delivery and eventually to play organized sports in zero gravity. The amount of intellectual property and value available in space is nearly unlimited. Although it would be nice to ignore the political ramifications of this device, they cannot be neglected. Which country is liable for the launches? Who is entitled to the taxes and intellectual property created in space? Should we continue to let certain laws such as the Launch Liability Treaty of 1972 and the Outer Space Treaty of 1967 continue to dominate the political agenda? Does a new Space Traffic Management Board need to be manifested? These are all questions that need to be answered before construction begins. The Antarctic Plateau, known as Ridge A, is also an interesting launch location because you get what we scientists call a sun-synchronous orbit. Plus, no single country owns the continent of Antarctica. And so now on to the more scientific portion of the presentation. Why do we need to build this device on top of Mount Everest? The most important reason is that the atmospheric pressure at this height is exponentially lower than that found at sea level. Another benefit is that the environment in this region is naturally cold. Coincidentally, this particular location is also good because the payload gains the momentum of the Earth's rotation near the equator, which is over 1,000 kilometers per hour at this latitude. Lastly, the gravity at this height is slightly lower, and the distance to space is slightly shorter. To prove this technology is not completely outside of the realm of reality, let us look at existing electromagnetic propulsion technologies. We use them every day in military applications, for transportation such as the maglev systems found in Asia. Scientific groups such as those found at the University of Stuttgart test Whipple shields hourly. And let's not forget about the immense amounts of energy that are used at facilities such as the CERN Particle Accelerator in Geneva, Switzerland. The LHC and other facilities of modern-day physics are able to accelerate particles to 95% the speed of light. What we need is just a single percentage of that velocity. I apologize for not knowing the original artist of this diagram. Please let me know if this illustration is yours so that I can give you acknowledgement in the future. I have, however, made some alterations from the initial design. As you can see, heat sinks and liquid nitrogen tanks have been added, as well as superconductors. Heat generated from each launch will likely be dissipated in a combination of light, chemicals, and basic heat diffusion. Few key aspects to take away from the original prototype are the distributed energy storage capacitors, generators, and autonomically controlled computerized timers, along with the silicon-controlled rectifier switches and cabling. Appropriate wiring, triggers, and sensors are also essential. It is critical that the payload hit the threshold speed of 7.8 kilometers per second so that it can reach an orbital trajectory. Approximately 30 billion joules of energy are used to launch a 1-ton package. The barrel is technically the most important piece of the superconducting coil gun because it presents the greatest physical hurdles. A mechanism must be put into place to stabilize the pressure and vibration created from the sonic boom as the projectile breaks the sound barrier and again when the bullet exits the gun. There needs to be a gradual increase in the number of air molecules inside the tube because moving from a vacuum into the atmosphere at 7.8 kilometers per second would be the equivalent of running directly into a brick wall, even though the pressure is only a fraction of that found at sea level. If possible, it would be nice to have an adjustable barrel, but at this point it is optional. What is not optional are the special materials used to prevent plasma erosion from forming on the inside of the tube. The gradual increase in G-load as the tube arcs upward is another important factor to consider in the final design. Lastly, the system must be 100% reliable, so some type of failover system must be put into place if one of the millions of power supplies or superconductors neglects to work or misfires. Here are some images I pulled from a few Sandia papers I found posted on the internet. The class of rocket used will be dependent upon the orbit which is selected and how much free mass is needed in the payload. It is likely that a new breed of small second-stage rockets will emerge. It is critical that this insertion rocket be mass-produced so that this portion of the launch costs no greater than $10,000 or 10,000 credits each. It is also important that these rockets have a reliability rate of ideally 99% because not all missions will have free weight for an emergency system if a rocket fails to fire and the satellite does not reach orbit. These are some rough estimates of the size, maximum temperature, and weight of the payload. Note that inside the superconducting materials on the exterior of the capsule, there is a thin sheet of mu metal that protects the contents of the interior from the electromagnetic field on the outside. Mu metal's unique nickel-iron compound has an extraordinarily high degree of magnetic permeability that is perfect for this application. Some of the more complex forces at hand are governed by the strange effects witnessed from superconductivity. Also, the coils of the gun function because of what are called eddy currents. I'm not going to claim to know all the physics behind solenoid tunnels or energy transfer, but I am quite certain that they will be both highly refined in the end product. There is another new technology called Doppler cooling, which was recently discovered by Dr. Stephen Chu, the current United States Secretary of Energy. This very interesting phenomenon, which won Dr. Chu the Nobel Prize, could play a key role in the launch system. Knowing the exact frequency of every molecule or group of molecules by using quantum physics could also be a necessary element in achieving launch perfection. Literally thousands upon thousands of consistent launches. The millions of switching apparatuses and cooling devices must be tested before the project can be fully brought online, after which point we can start looking at different staging opportunities such as ion propulsion. This is a very generic diagram that I came up with to show how each variable interacts with one another. We start on the outside with the physical constraints such as the acceleration, frequency of launches, and weight of the payloads, but eventually everything leads to the bottom line, the cost, which if you remember correctly is only $100 billion. I would like to take this opportunity to thank the following individuals and organizations. The International Space University for teaching me the majority of what I know about the space industry, Dr. Mino Freund of NASA Ames, Dr. Nikolai Telerenko, my good Norwegian friend Ulla Western, Gary Martin, my father Robert Park, the Robert Heinlein Foundation, and most importantly the Internet, without which I would have never found the materials used in this presentation. I would like to thank you for your time. I hope that I have helped you realize that we are literally on the verge of space.